In the vacuum between stars, where no wind stirs and no sound travels, the human body does not decay, it drifts, preserved in ways that seem almost impossibly gentle, held in a kind of stillness that Earth has never known. There is something strangely peaceful in understanding what the cosmos would do with us, how the cold and the emptiness would treat this fragile architecture of bone and breath, not with violence, but with a quiet, patient transformation that unfolds across years, perhaps centuries, in the endless dark. If these slow journeys into curious corners of existence bring a sense of calm, leaving a subscription ensures more such evenings will find their way to you. The body floats, tumbling in imperceptible rotations, and the story of what happens next, the freezing, the sublimation, the slow work of radiation, begins here, in the silence between worlds. In the summer of 1966, somewhere within the sprawling administrative corridors of the National Aeronautics and Space Administration, a document was quietly circulated among a small group of officials and medical advisors. Bearing the rather clinical heading of Crew Remains Disposal Considerations for Extended Duration Spaceflight, and though the memo itself has long since been filed away in some archive or another, its existence speaks to a question that was beginning to stir in the minds of those responsible for sending human beings beyond the thin blue envelope of Earth's atmosphere. A question that nobody particularly wanted to raise at dinner parties or press conferences, but which nonetheless demanded, in its patient and unhurried way, some manner of official consideration. You see, by the middle of that decade, space travel had ceased to be a purely theoretical endeavor and had become instead a rather practical matter of engineering and logistics and, inevitably, contingency planning. And when one begins to plan for contingencies in earnest, one must eventually arrive at the contingencies that involve the absence of a heartbeat, the cessation of breath, the transformation of a crew member from a living participant in the mission to something else entirely, something that still occupies space and mass but no longer answers when called upon. Just 1 year earlier, in March of 1965, a Soviet cosmonaut by the name of Alexei Leonov had floated out of the airlock of the Voskhod 2 spacecraft and into the silent emptiness beyond, becoming the first human being to conduct what we now call a spacewalk. And though the mission was celebrated as a triumph, those who understood the engineering involved knew that Leonov had come rather close to not returning at all, as his suit had ballooned in the vacuum to such a degree that he struggled to re-enter the airlock, and for several long minutes the tether connecting him to his spacecraft was the only thing preventing him from drifting away into an orbit of his own, alone and beyond any possibility of retrieval. The tether held, as it happened, and Leonov returned to Earth to receive his medals and give his interviews. But the engineers and flight surgeons on both sides of the space race understood that this outcome was not guaranteed, that a frayed cable or a failed carabiner or a simple miscalculation could result in a cosmonaut or astronaut floating away from their spacecraft at a relative velocity of only a few centimeters per second, which sounds quite gentle until one realizes that in the vacuum of space there is no friction to slow this drift, no medium to push against, no way to swim or flail one's way back to safety, and so that gentle velocity would carry them onward until the oxygen in their suit ran out, and then for a very long time afterward. This was the unspoken fear that prompted the 1966 memo, and it was the same fear that would, just 2 years later, inform the language of Article 5 of the Outer Space Treaty, which was signed by the major spacefaring nations in 1967 and which included, among its various provisions concerning the peaceful use of outer space, a rather somber clause stating that parties to the treaty should return to the launching state the remains of personnel of a spacecraft found in their territory, which sounds straightforward enough until one considers the vastness of space and the practical difficulties involved in locating and retrieving a body that might be tumbling along in its own private orbit around the Sun, gradually moving farther from any other human artifact with each passing year. The following year, in 1968, an aerospace physician by the name of Dr. Emanuel Roth published a paper in a specialized medical journal, bearing the title Cadaver Disposition in Extraterrestrial Environments, and though the paper received little attention from the general public, it represented one of the first serious attempts to consider, in a methodical and scientific manner, what might actually happen to a human body exposed to the conditions of space, and what options might be available to mission planners who found themselves in the unfortunate position of having to decide what to do with the remains of a fallen colleague when burial at sea was not an option and burial at land was several 100,000 kilometers away. Dr. Roth's paper approached the subject with the sort of detached clinical curiosity that one finds in the best medical literature, noting that the traditional concerns of terrestrial forensic medicine, such as decomposition and insect activity and the various microbial processes that return a body to the earth from which it came, would operate very differently or not at all in the vacuum of space, and that new considerations, such as sublimation and radiation exposure and the absence of oxidative chemistry, would take their place, though the precise rates and mechanisms remained somewhat speculative in the absence of experimental data that nobody was particularly eager to collect. Meanwhile, in the summer of 1969, as the Apollo 11 mission prepared to land the first human beings on the surface of the Moon, a speechwriter named William Safire was asked by the Nixon administration to prepare a statement for the president to deliver in the event that the mission ended in catastrophe, specifically in the event that Neil Armstrong and Edwin Aldrin successfully landed on the lunar surface but were unable to lift off again, stranding them on the Moon with no possibility of rescue, their oxygen slowly depleting as the world watched and waited and could do nothing at all to help. The speech, which was never delivered but which survives in the archives, began with the words that fate has ordained that the men who went to the Moon to explore in peace will stay on the Moon to rest in peace, and it went on to speak of brave men who knew there was no hope for their recovery but who also knew that there was hope for mankind in their sacrifice. And while the language was moving in its way, it also served as a reminder that the officials responsible for the space program had thought quite carefully about the possibility of leaving human remains in extraterrestrial locations, not because they wished to do so but because the nature of the endeavor made such outcomes possible and planning for them necessary. What the speech did not describe, and what the contingency protocols could not address, was the question of what would happen next, in the hours and days and years following such a tragedy, to the physical forms of the astronauts themselves, whether on the Moon or, in another scenario that was equally plausible, adrift in the space between worlds, released intentionally or accidentally from a spacecraft and left to whatever fate awaited them in the endless dark. And this brings us to the operational reality of space missions, which is that spacecraft are small and resources are limited and the mission must continue if it can. And so the official NASA protocol for dealing with a crew member who died during a mission was, at its core, quite simple in its stark practicality. You close the hatch, and you continue the mission, because there is nothing else to be done. Because the living have responsibilities to themselves and to mission control and to the taxpayers who funded the endeavor, and because grief, however profound, cannot be permitted to compromise the safety of those who remain. This protocol was not cruel in its intention, though it may sound rather cold when stated plainly, but was instead a recognition of the fundamental constraints of spaceflight, where every kilogram of mass must be accounted for and every cubic meter of volume serves a purpose and there is simply no room, either literally or figuratively, for extended mourning rituals or elaborate preservation procedures. And so the departed would be placed somewhere out of the way, in an airlock or a storage compartment, or in some scenarios released into space itself, and the mission would proceed, because that is what missions do. But the question remained, quiet and patient and waiting to be asked by those with sufficient curiosity and sufficient detachment to consider it without flinching. Which was this: what would actually happen, in a physical and chemical and biological sense, to a human body that was released into the vacuum of space, not in the dramatic manner of science fiction, with explosive decompression and instant freezing and all the theatrical flourishes that cinema has taught us to expect, but in the slow and methodical manner of actual physics, operating according to principles that do not care whether we find them comforting or disturbing, proceeding at their own unhurried pace through the hours and days and centuries that would follow. To begin to answer this question, one must first understand the environment in which such a body would find itself, and that environment is rather different from what our intuitions might suggest, because space is not simply cold in the way that a winter's night is cold, with air temperatures that can be measured by a thermometer held up to the wind, but is instead a near-perfect vacuum, containing on average only a few atoms per cubic centimeter, which is to say that there is almost nothing there at all for heat to conduct into, almost no medium for temperature in the conventional sense to have any meaning. And yet there is a temperature to empty space, or rather there is a temperature to the radiation that fills empty space, which is the cosmic microwave background, the faint afterglow of the Big Bang that occurred some 13.8 billion years ago and which has been cooling ever since, stretching out into longer and longer wavelengths as the universe expands, until now it corresponds to a temperature of approximately 2.7 Kelvin, which is to say 2.7 degrees above absolute zero, which is very cold indeed by any terrestrial standard. This cosmic microwave background is, in a sense, the universe's ambient warmth, the base temperature that all objects in deep space would eventually reach if left alone for long enough, radiating away their own heat into the darkness until they came into thermal equilibrium with that faint bath of ancient photons. And it is against this background, in this environment of near-nothingness and ancient light, that our question must be considered, as we follow, molecule by molecule and process by process, the slow transformation of a human form released into the endless dark. The journey from living body to whatever remains at the end of cosmic time is not a dramatic one, in the theatrical sense, but it is a journey nonetheless, with stages and transitions and processes that proceed according to the laws of physics and chemistry, laws that operate with the same quiet indifference whether they are acting upon a stone or a spacecraft or the body of someone who once breathed and thought and looked up at the stars with wonder. And it is this journey that we shall now consider, not with morbid fascination but with the gentle curiosity of those who wish to understand how things work, even the things that we would prefer not to think about too closely. So let us begin, in the manner of a bedtime story that happens to concern thermodynamics and vacuum physics and the long slow processes of cosmic time, by considering what happens in the first moments after exposure, when the hatch closes behind and the stars stretch out ahead, and the body begins its transition from the warmth of life to the cold equilibrium of eternity, one gentle step at a time, with no hurry at all, because space has nothing but time, and the processes we shall describe have all the patience in the universe. And so we come now to consider what happens here, on our own familiar Earth, when a body is no longer living, when the breath has stopped and the heart has grown still, and all the countless processes that kept a person animated and aware have quietly ceased their work. This is not a morbid consideration. Not truly, but rather a natural one. A part of the great cycling of matter and energy that has continued on our planet for billions of years. And understanding what happens here, in the embrace of our atmosphere and our soil and our teeming microscopic companions, will help us appreciate just how different things become when a body finds itself suspended in the void between worlds, where none of these familiar processes can unfold in quite the way they do at home. On Earth, you see, decomposition is fundamentally a collaborative effort, a kind of slow and patient teamwork undertaken by countless organisms, from the bacteria that have lived within us all along to the insects that arrive with remarkable punctuality, to the fungi and the larger scavengers, and ultimately the very chemistry of the soil itself. A body returned to the earth is not abandoned but rather welcomed, in a sense, by a vast community of living things that have evolved over millions of years to make use of precisely this kind of material, to break it down and recycle its components and return its atoms to the great circulating pool from which new life will eventually emerge. This is what happens in the embrace of our world, and it begins, as so many things do, at the very smallest scale, within the cells themselves. When a person dies, when the heart stops beating and the lungs no longer draw breath, the body's 37 trillion cells do not all cease functioning at the same instant. Rather, death proceeds as a kind of gradual wave, spreading through tissues at different rates depending on their metabolic needs and their sensitivity to the sudden absence of oxygen. The brain, which consumes so much of our body's energy and oxygen supply, begins to suffer within mere minutes, its neurons unable to maintain the delicate electrochemical gradients that allow them to function. Within approximately 4 minutes of oxygen cessation, brain cells begin to die in earnest, though some tissues, those with lower metabolic demands, may persist in a kind of diminished functioning for considerably longer. This is why the window for resuscitation is so narrow, why those first few minutes are so critical in emergency medicine, because the brain's sensitivity to oxygen deprivation means that meaningful recovery becomes increasingly unlikely as time passes. But what happens next, in those hours and days after death, is something that researchers have studied with great care and considerable patience, and perhaps no institution has contributed more to our understanding of this process than the Anthropological Research Facility at the University of Tennessee in Knoxville, which was founded in 1981 by a forensic anthropologist named Dr. William Bass. This facility, which has come to be known colloquially as the Body Farm, was established specifically to study human decomposition under a variety of conditions, to observe and document and quantify what happens to human remains when they are left in different environments, whether exposed to sun or shade, whether placed on the surface or buried at various depths, whether in water or in vehicles or in any of the countless situations that forensic investigators might encounter in their work. The knowledge gained at this facility and others like it has proven invaluable in helping investigators establish time of death, in solving crimes, in bringing closure to families, but it has also given us a remarkably detailed picture of decomposition itself, of the predictable sequence of changes that a body undergoes when the breath has stopped and the living processes have given way to other kinds of activity. Among the researchers who have contributed to this understanding is Dr. Arpad Vass, a forensic anthropologist who worked for many years at Oak Ridge National Laboratory and who developed a framework for understanding decomposition as proceeding through approximately 8 distinct stages, each characterized by particular changes in the body's appearance and chemistry, and each occurring within a roughly predictable time frame, Though of course the exact timing depends enormously on environmental conditions such as temperature and humidity and the presence or absence of insects and other organisms. This 8-stage decomposition timeline provides a kind of map of the territory, a way of understanding the predictable sequence of changes that transform a recently deceased body into something very different over the course of days and weeks and months. The first of these changes, the very earliest processes of decomposition, begin not with the arrival of external organisms but with a phenomenon called autolysis, which means, quite literally, self-digestion. Within the cells of the body, you see, there exist small membrane-bound compartments called lysosomes, which contain powerful digestive enzymes capable of breaking down proteins and lipids and other cellular components. In life, these enzymes are kept carefully contained within their membranes, safely separated from the rest of the cell, where they perform useful functions such as breaking down damaged organelles or foreign materials that the cell has engulfed. But when a cell dies, when its energy supply fails and it can no longer maintain the integrity of its membranes, these lysosomes begin to leak, and their digestive enzymes spill out into the surrounding cellular material, and they begin to break down the very cell that once contained them. This is autolysis, and it begins within hours of death, and it proceeds entirely without the involvement of any external organisms, driven purely by the body's own enzymes turning upon themselves in the absence of the regulatory mechanisms that once kept them in check. But autolysis is only the beginning, only the first quiet stirrings of decomposition, because a living human body is not, strictly speaking, a single organism at all, but rather a kind of ecosystem, a community of trillions upon trillions of cells, not all of which are human. Within our digestive tracts, upon our skin, in our mouths and respiratory passages, there live approximately 100 trillion bacteria, give or take, a number so vast that bacterial cells actually outnumber human cells in our bodies by a considerable margin. In life, these bacteria are our partners, our symbionts, helping us digest food, producing vitamins, competing with potentially harmful organisms for space and resources, and generally contributing to our health in ways that researchers are only beginning to fully appreciate. But when we die, when the immune system ceases its vigilant patrol and the intestinal walls begin to break down through autolysis, these bacteria are no longer confined to their usual habitats, and they begin to spread throughout the body, and they begin to consume it. Among the most active of these internal decomposers are bacteria from the genera Clostridium and Bacillus, which are particularly well suited to the environment inside a decomposing body. Clostridium bacteria are anaerobic, meaning they thrive in the absence of oxygen, and the interior of a body, even one exposed to air, quickly becomes an oxygen-poor environment as the remaining oxygen is consumed by aerobic bacteria and chemical reactions. These Clostridium bacteria produce enzymes that break down proteins, releasing gases as byproducts, gases that cause the characteristic bloating of a decomposing body and that carry the distinctive odors associated with putrefaction. Bacillus bacteria, meanwhile, can form hardy spores that allow them to survive adverse conditions, and they too contribute to the breakdown of tissues through their metabolic activities. Together, these and countless other bacterial species transform the body from within, turning solid tissues into liquids and gases, breaking down the complex molecules of life into simpler compounds. And then, of course, there are the insects. On Earth, in most environments, insects arrive at a body with remarkable speed and predictability, often within minutes of death if conditions allow. Flies are typically the first to arrive, particularly blowflies of the family Calliphoridae, which can detect the chemical signatures of death from considerable distances and which lay their eggs in the natural openings of the body, in the eyes and mouth and nose, where the emerging larvae will find ready access to soft tissues. These larvae, these maggots, are extraordinarily efficient consumers of flesh, and a large population of them can reduce a body to bones with startling rapidity, their combined metabolic heat sometimes raising the temperature of the surrounding tissues by 10 or 15 degrees Celsius above ambient conditions. After the flies come beetles, particularly those of the families Sylphidae and Domestidae, the carrion beetles and skin beetles, which prefer drier conditions and which consume the tougher tissues that the fly larvae leave behind. And throughout this process, depending on the environment, larger scavengers may also participate, from birds and small mammals to, in some regions, larger carnivores, each playing their role in the great recycling of organic matter. All of this bustling activity and chemical transformation depends upon conditions that we take for granted here on Earth, conditions that seem so ordinary and ubiquitous that we rarely pause to consider them, but which are in fact remarkable and specific and utterly absent in the void of space. On Earth, there is atmosphere. There is oxygen for the aerobic bacteria that initiate much of the decomposition process. There is humidity to keep tissues moist and pliable and accessible to enzymatic activity. There is warmth, at least in most environments and most seasons, to drive the chemical reactions that break down complex molecules. And there is, perhaps most importantly, an entire living world of organisms ready and eager to participate in the decomposition of organic matter, from the bacteria already present in the body to the insects that arrive from without to the fungi and scavengers and all the rest. In space, none of this is true. There is no atmosphere, and therefore no oxygen for aerobic bacteria to use in their metabolic processes. There is no humidity, and indeed any moisture present in exposed tissues would rapidly sublimate away into the vacuum. There are no insects, no scavengers, no fungi floating on the solar wind waiting to colonize organic matter. The internal bacteria might persist for a time, particularly the anaerobic species like Clostridium that do not require oxygen, but even they would face conditions unlike any they evolved to tolerate, conditions of extreme cold and radiation and the gradual desiccation of the very medium in which they live. Space, in short, offers none of the collaborators that decomposition requires on Earth, none of the partners in the great work of recycling that has continued on our planet for as long as there has been death. And here we might pause to consider a curious parallel, an earthly phenomenon that offers a hint, just a hint, of what might happen to a body in an environment that lacks the usual agents of decomposition. In the deserts of Egypt, in the arid sands that border the Nile, ancient bodies have been discovered that were preserved not through deliberate mummification but simply through the action of the dry environment itself. These natural mummies, dating back thousands of years, show us what aridity alone can do to human remains, how the rapid desiccation of tissues can halt the processes of decay before they have truly begun, how the removal of water, which is essential for bacterial activity and enzymatic reactions, can preserve flesh and skin and hair and even internal organs for millennia. The ancient Egyptians observed these natural mummies, scholars believe, and were inspired by them to develop their elaborate techniques of artificial preservation, their rituals of embalming and wrapping that produced the famous mummies we know from museums and documentaries. But the natural mummies came first. preserved by nothing more than heat and dryness and the absence of the moisture that decay requires. Space, in a sense, is the ultimate desert, colder and drier and emptier than any environment on Earth, more hostile to the processes of decomposition than any place our planet has to offer. And so as we turn our attention outward, as we consider what would happen to a human body adrift in that vast and silent emptiness, we carry with us this understanding of earthly decomposition, this knowledge of the bacteria and insects and chemical processes that transform the dead on our home world. And we prepare ourselves to discover how utterly different things become when all of these familiar agents are stripped away, leaving only the body itself and the implacable physics of the void. Let us settle now into the first hours, those quiet opening moments when a human body finds itself adrift in the deep vacuum of space, far from atmosphere, far from pressure, far from the gentle envelope of gases that we so rarely think about here on Earth. This is not a dramatic tale, despite what films might have you believe, but rather a series of quiet physiological changes, each one following logically from the last, each one governed by the simple physics of pressure and temperature and the behavior of fluids in conditions we seldom encounter. So let your breathing slow, let your shoulders drop, and we shall walk through these processes together at a gentle pace, understanding each step as we go. The vacuum of space is, at its heart, simply an absence of air, an absence of pressure, an absence of the molecular bustle that surrounds us here at sea level. Our bodies have evolved over millions of years to exist within a very narrow band of atmospheric conditions, roughly 1 atmosphere of pressure, which is to say about 14.7 pounds pressing on every square inch of our skin at all times. We do not feel this pressure because it pushes equally from all directions and because the fluids within our bodies push back with equal force. But remove that external pressure, as happens when a body enters the vacuum of space, and the equilibrium shifts in ways that are gradual and, in their own manner, rather gentle. The pioneering research into what happens to biological tissue in near-vacuum conditions began in earnest during the early space age, when scientists needed to understand the risks astronauts might face should their spacecraft or suits lose integrity. In 1965, researchers at Brooks Air Force Base in Texas conducted a series of careful experiments using chimpanzees as subjects, exposing them to rapid decompression to pressures equivalent to the near vacuum found at extreme altitudes. These studies, while difficult to contemplate from an ethical standpoint today, provided essential data about survivability and the sequence of physiological events that follow sudden pressure loss. The chimpanzees, it was found, could survive brief exposures to near-vacuum conditions provided they were recompressed within roughly 90 seconds to 2 minutes, and the data gathered informed NASA's understanding of emergency scenarios and rescue timelines for human spaceflight. One of the phenomena these researchers studied bears the gentle name of ebullism, which refers to the formation of gas bubbles within body fluids when external pressure drops below a critical threshold. This is not quite the same as boiling in the kitchen sense, though the underlying principle is related. You see, any liquid will begin to vaporize when the pressure above it drops below its vapor pressure at a given temperature. Here on Earth, water boils at 100 degrees Celsius because that is the temperature at which water's vapor pressure equals our atmospheric pressure. But lower the atmospheric pressure and water will boil at progressively lower temperatures. This relationship was explored in a 1966 paper published in the journal Aerospace Medicine, which examined ebullism thresholds and the conditions under which body fluids would begin to vaporize at physiological temperatures. There exists a boundary in our atmosphere called the Armstrong line. named after Harry George Armstrong, a United States Air Force physician who contributed greatly to aerospace medicine. This line sits at approximately 63,000 feet above sea level, or about 19 kilometers, where atmospheric pressure has dropped to roughly 6% of sea level pressure. At this altitude, the pressure is so low that water, and therefore the fluids in your body, will begin to boil at 37 degrees Celsius, which is, of course, normal human body temperature. Above this line, an unprotected human body would experience ebullition, with dissolved gases coming out of solution in the blood and water beginning to vaporize in the tissues. The Armstrong line represents, in a sense, the edge of survivability without a pressurized suit or cabin, and beyond it lies the regime where vacuum effects become dominant. Now, let us consider what actually happens in those first seconds when a human body is exposed to vacuum. Perhaps the clearest account we have comes from an accident that occurred at NASA in 1966, involving a technician named Jim LeBlanc. During a test of a prototype spacesuit in a vacuum chamber, a hose connection failed and the suit rapidly depressurized while LeBlanc was inside. The pressure dropped to less than 1 psi within seconds, effectively exposing him to near-vacuum conditions. In the accounts that followed, LeBlanc described remaining conscious for approximately 14 seconds, during which time he recalled the distinctly odd sensation of the saliva on his tongue beginning to bubble and boil. This was not a painful boiling but rather a fizzing, effervescent feeling as the moisture vaporized at the low pressure. He then lost consciousness, and his colleagues initiated emergency repressurization, restoring the chamber to survivable pressure within roughly 30 seconds. LeBlanc recovered fully, experiencing no lasting damage, and his account remains one of the very few first-hand descriptions of vacuum exposure in a human being. NASA's research and estimates suggest that consciousness persists for approximately 9 to 11 seconds following sudden exposure to vacuum. This brief window exists because the brain can function for a short time on the oxygen already dissolved in the blood and present in the brain tissue itself. However, without fresh oxygen being delivered, and with blood pressure dropping as gases expand and circulation falters, unconsciousness follows swiftly. It is a quiet fading rather than a dramatic collapse, much like the gentle dimming one might experience at the onset of a faint, a narrowing of vision and awareness that precedes a soft descent into darkness. One of the most persistent misconceptions about vacuum exposure, perpetuated by countless films, is the notion that the body would explosively decompress, bursting outward in a violent spray. This simply does not occur. Human skin is remarkably elastic and quite strong, well capable of containing the internal pressure of our bodies even when external pressure drops to zero. The body would indeed swell as gases within tissues expand and as water vapor forms in the softer parts, but this swelling is gradual and contained. Research and accident data suggest that the body might expand to roughly twice its normal volume, a gentle puffing outward that affects the limbs and torso but does not rupture the skin. The circulatory system, being a closed loop of blood vessels, contains the blood effectively, and while gas bubbles might form in the veins and impede flow, the catastrophic ruptures of cinema are purely fictional. You may rest easy knowing that the reality is far more subdued. In those first hours adrift in the void, the body would undergo a quiet process of desiccation, a gradual loss of moisture from the surfaces exposed to vacuum. The eyes, being moist and delicate, would begin to lose water through sublimation, which is the direct transition from liquid to gas without passing through a liquid to gas boiling phase. though in practice the distinction blurs at these pressures. The moisture on the surface of the eyes would simply drift away as vapor, leaving the tissues increasingly dry. The mouth and airways, similarly moist, would lose water in the same fashion, the tongue and throat gradually desiccating as hours passed. This is the beginning of a natural freeze-drying process, the same principle used to preserve foods for long storage, and it would proceed slowly, quietly, without drama or violence. One might expect that a body in space would freeze solid very quickly, given how cold the void is often described to be. But this expectation misunderstands the nature of heat transfer. Temperature, in the everyday sense, requires matter to conduct it, molecules bumping into one another and transferring energy. In the vacuum of space, there are no molecules, or so few that they are negligible, and therefore no conduction can occur. A body cannot lose heat by conduction to the vacuum because there is nothing there to conduct heat away. Nor can convection occur, as convection requires a fluid medium, a gas or liquid, to carry heat away through bulk motion. The only remaining mechanism for heat loss is radiation, the emission of infrared energy from the body's surface, and this is a relatively slow process. The human body, at its normal temperature of 37 degrees Celsius, radiates heat at a modest rate determined by the Stefan-Boltzmann law, which relates radiated power to the fourth power of absolute temperature. At body temperature, this works out to a few hundred watts of radiated power, which sounds like quite a lot until you consider that the body has considerable thermal mass and that this heat is being lost only from the surface. A rough calculation suggests that a body in vacuum, starting at normal temperature, would take many hours to cool significantly through radiation alone. The core temperature would drop slowly, perhaps a degree or two per hour initially, with the rate decreasing as the body cooled and the temperature difference between body and surroundings diminished. This means that in the first hours, the body remains relatively warm internally, even as the surface begins to cool and moisture sublimates away. The interplay of these processes, the gentle swelling, the slow desiccation, the gradual radiative cooling, creates a quiet tableau rather different from the violent images of fiction. The body drifts, slowly rotating perhaps if it was imparted any spin at the moment of exposure, tumbling gently in the silence. The limbs may stiffen slightly as gases expand in the joints, but they do not flail or contort. The face may swell, the tongue may protrude slightly as tissues puff, but the overall form remains recognizably human. There is no sound in vacuum, of course, so whatever internal gurglings or shifts might occur happen in perfect silence, unheard and unheralded. The eyes, losing moisture steadily, would grow cloudy as the corneas desiccated, the delicate transparency giving way to an opaque dullness over the course of hours. The lips would crack and dry, the moisture that normally keeps them supple drawn away into the void. Inside the body, the situation is more complex, with tissues at different depths experiencing different rates of change. The skin, being the outermost layer, loses moisture fastest and may begin to take on a leathery quality even in these early hours. Deeper tissues, insulated by the body's own mass, change more slowly, the internal organs remaining relatively moist and intact while the surface transforms. It is worth pausing to appreciate how thoroughly our existence depends on the thin shell of atmosphere that clings to our planet. We move through our days rarely thinking about the 14.7 pounds per square inch pressing on us from all sides. rarely considering that our blood remains liquid only because that pressure keeps it so, rarely acknowledging that our eyes stay moist and our lungs function only within this narrow band of conditions. The human body is a marvel of adaptation to Earth's environment, but it is precisely that, an adaptation, finely tuned to one particular set of circumstances. Remove those circumstances and the body responds in predictable ways, following the laws of physics with the same inevitability as water flowing downhill. The researchers at Brooks Air Force Base and the physicians who documented Jim LeBlanc's accident were not engaged in morbid curiosity but in the practical work of keeping astronauts safe. Understanding what happens in vacuum exposure allowed NASA to design better suits, better emergency protocols, better rescue procedures. The 14-second window of consciousness that LeBlanc experienced became a crucial design parameter, informing how quickly spacecraft systems needed to respond to depressurization events. The knowledge that skin contains pressure well and that the body does not explode allowed engineers to focus on the real risks: the hypoxia, the ebullism, the circulatory disruption, rather than imaginary ones. As we conclude this section on the first hours, let your mind settle into the understanding that these processes, while perhaps unsettling to contemplate in waking hours, are simply the body following physical law. There is no malice in vacuum, no cruelty in the void, only the absence of conditions to which we are adapted. The body swells gently, cools slowly, dries gradually, and drifts in silence, a quiet transformation governed by the same principles that shape stars and planets and the gaps between them. And with that understanding, let us breathe slowly, let our thoughts soften, and prepare to move forward into the longer timescales of what follows, knowing that each step is merely physics unfolding in its patient, unhurried way. And so we come now to the quieter phase, the longer waiting, where time stretches out in ways that are difficult for us to truly comprehend, and the body begins its slow transformation into something that will endure far longer than any of us might expect. This is the phase of preservation, of gradual change measured not in hours or days but in months and years and perhaps even centuries. And it begins with a process that you may recognize from your morning cup of coffee, though you have likely never thought of it in quite this way. The process is called sublimation, and it describes the rather elegant phenomenon whereby a solid transforms directly into a gas without ever passing through the liquid phase that we might ordinarily expect. You see, under normal circumstances here on Earth, when ice warms, it melts into water, and when that water warms further, it evaporates into vapor, and this progression from solid to liquid to gas feels so natural to us that we rarely question whether it must always be so. But it need not always be so, and under certain conditions, the liquid phase is skipped entirely, and the solid simply vanishes into vapor as though the intermediate step were merely optional, which in a sense it is. The key to understanding this lies in atmospheric pressure, that gentle weight of air pressing down upon us and upon everything around us, a pressure so constant and so familiar that we forget it exists at all. Here at sea level, we experience roughly 1 atmosphere of pressure, and under this pressure, water behaves in the orderly fashion we have come to expect, freezing at 0 degrees Celsius and boiling at 100. But if we reduce that pressure significantly, the rules begin to change, and water finds new ways to move between its phases. Consider the freeze-drying process used to create instant coffee, that curious powder that transforms back into something resembling coffee when you add hot water. The coffee is first frozen, as you might expect, But then it is placed in a chamber where the pressure is reduced to approximately 0.06 atmospheres, which is to say about 6% of the pressure we experience at sea level. At this low pressure, the ice within the frozen coffee does not melt into water but instead sublimes directly into vapor, leaving behind the dried solids that make up the powder you spoon into your cup. The coffee is preserved because the water has been removed without ever becoming liquid, without ever providing the medium in which bacteria might thrive and cause decay. Now, space operates on similar principles, though far more extreme. The pressure in the vacuum of space is not 0.06 atmospheres but essentially zero, so close to nothing that we measure it in units so small they become almost meaningless to our everyday understanding. In this environment, any ice that forms will sublime away given sufficient time and energy, transitioning directly from solid to vapor and drifting off into the void. And so the frozen moisture within a body adrift in space will gradually, very gradually, make this same transition, not melting into liquid decay but vanishing particle by particle into the emptiness. The British astronomer Fred Hoyle, who contributed so much to our understanding of how elements are formed within stars, also devoted considerable thought to the question of how organic materials behave in the vacuum of space. His research suggested that the absence of atmospheric pressure, combined with the absence of liquid water and the intense cold, creates conditions remarkably favorable for preservation. Without water in its liquid form, the chemical reactions that drive decomposition simply cannot proceed in their usual fashion, and materials that would quickly break down on Earth may persist in space for extraordinarily long periods. Dr. Hoyle's work touched on many aspects of how organic compounds might survive and travel through the cosmos, and while some of his ideas remained controversial, his observations about preservation in vacuum have been supported by subsequent research and observation. To understand how effectively cold and dryness can preserve a body, we need only look to certain places here on Earth where similar conditions exist. Places where the air is thin and cold and remarkably free of moisture. High in the Andes Mountains of Argentina, near the summit of Mount Lulayaco at an elevation of 6,739 meters, archaeologists discovered something extraordinary in 1999. There, in a stone structure built by the Inca people more than 500 years ago, they found the preserved bodies of 3 children, sacrifices from a ritual known as capacocha, and these bodies were not skeletons but remarkably intact mummies, their skin and hair and internal organs preserved to a degree that astonished the researchers who found them. The children of Lulayaco had been preserved by the same principles we have been discussing, though on a mountaintop rather than in space. At that extreme altitude, the atmospheric pressure is significantly reduced, and the air is bitterly cold and extraordinarily dry. The bodies had frozen soon after death, and in the centuries that followed, the moisture within them had gradually sublimed away, the ice transitioning directly to vapor in the thin, cold air. No liquid water had ever formed within the tissues. No bacteria had found the conditions suitable for growth and reproduction, and so the bodies had simply waited, unchanging in any way perceptible to human observation, until they were found half a millennium later. The preservation was so complete that researchers could observe details of the children's final hours, could see the food they had eaten, could examine their clothing and hair and the objects placed beside them. One of the children, a girl of approximately 15 years, was found in such a state of preservation that she appeared merely to be sleeping, her features peaceful and intact, her skin still bearing its natural color in places. This is what cold and dryness can do. This is how effectively the absence of liquid water can halt the processes of decay, and space offers these conditions in their most extreme form. But what of the bacteria themselves? Those microscopic organisms that would normally begin breaking down a body from within almost immediately after death. Here we must consider what happens to these tiny creatures when they are suddenly exposed to the vacuum of space. And the answer is somewhat reassuring for our purposes, which is to say that most of them die quite promptly. NASA conducted extensive studies in 2005 examining the survival of various microorganisms in conditions simulating the space environment, and the results confirmed what earlier research had suggested. The combination of vacuum, extreme temperature fluctuations, and intense radiation proves lethal to the vast majority of bacterial life. Some hardy spore-forming bacteria can survive in a dormant state, their metabolism suspended and their cellular processes halted, but they cannot actively grow and reproduce in these conditions. They simply wait. As the body waits, neither living nor dying in any active sense. The radiation environment of space is particularly hostile to microbial life. Cosmic rays and unfiltered solar radiation damage cellular structures and genetic material in ways that most organisms cannot repair. And while some microbes can survive brief exposure, extended time in open space proves fatal to nearly all of them. The bacteria that might have begun decomposing a body on Earth find themselves killed by the same environment that killed their host. And so the natural process of decay is interrupted at its very source. There is, however, a remarkable exception to this general rule of microbial death in space, an exception so extraordinary that it deserves mention here. In 2007, the European Space Agency conducted an experiment called Biopan on the Photon M3 mission, in which various organisms were exposed to the full space environment outside the spacecraft for 10 days. Among the organisms tested were tardigrades, those microscopic creatures sometimes called water bears, and the results were quite remarkable. Tardigrades are known for their ability to survive extreme conditions by entering a state called cryptobiosis, in which their metabolism essentially stops and they become extraordinarily resistant to environmental stresses. In the Photon M3 experiment, some tardigrades survived not only the vacuum of space but also exposure to unfiltered solar radiation, and upon return to Earth and rehydration, they revived and resumed their normal activities, including reproduction. This demonstrates that while space is hostile to most life, it is not universally lethal, and some organisms have evolved mechanisms to endure what would kill nearly any other creature. For our purposes, however, the relevant point is that the bacteria responsible for decomposition are not tardigrades. They lack these remarkable survival mechanisms, and in the space environment, they die or become dormant quite quickly, leaving the body free to undergo its slow transformation without their participation. And so the mummification begins. With the initial swelling subsided, with the surface ice subliming away into vapor, with the bacteria killed or dormant, the body enters a phase of gradual desiccation that may continue for months or years or even decades. The process works from the outside in, as you might expect, with the outer tissues losing their moisture first and becoming dry and leathery while the deeper tissues retain their ice for longer. The skin, being the outermost layer, desiccates first, losing its moisture to the vacuum and becoming tough and rigid, somewhat like leather that has been left to dry in the sun. This dried outer layer actually slows the sublimation of the ice beneath it, creating a kind of protective shell that extends the overall process. The tissues beneath continue to lose their moisture, but more slowly now, the vapor having to find its way out through the increasingly dried outer layers. Over months, this process continues, the body gradually shrinking as the water that once made up so much of its mass vanishes into space. The features become drawn and angular as the soft tissues beneath the skin desiccate, and the body takes on the appearance that we associate with ancient mummies, though achieved through a different mechanism than the deliberate mummification practiced by the Egyptians or other cultures. This is natural mummification, freeze-drying on a timescale measured in months and years rather than the hours required in industrial processes. There is a certain irony here that seems worth noting, a quiet paradox in the relationship between destruction and preservation. The vacuum of space is profoundly hostile to human life, capable of killing an unprotected person in minutes through mechanisms we have already discussed. And yet this same environment, having killed, becomes extraordinarily effective at preserving what it has killed. The conditions that make survival impossible also make decay impossible, and so the body that could not live in space for even a few minutes may persist there for thousands of years, perhaps longer, a kind of monument to both the fragility and the durability of human physical form. The timeline for complete mummification depends on several factors that would vary from one case to another. A body in direct and continuous sunlight would sublime more quickly, the thermal energy driving the transition from ice to vapor at a faster rate. A body tumbling in space, alternately heated and cooled as it rotates through light and shadow, might mummify more slowly, the ice having time to stabilize during the cold periods. The initial moisture content of the body matters as well, and the body composition, and the particular orbital characteristics that determine exposure to solar radiation. Conservative estimates suggest that full mummification, the complete desiccation of all tissues to a stable, leather-like state, might take anywhere from several months to several decades. The process is gradual and continuous, with no dramatic transitions or sudden changes. Just the slow, steady loss of moisture to the vacuum, particle by particle, molecule by molecule, until what remains is dry and light and remarkably stable. And once this mummification is complete, the body has entered a state of preservation that might endure for immense stretches of time. Without water, without active bacteria, without the chemical reactions that drive decomposition on Earth, the mummified remains will simply drift through space, slowly tumbling perhaps, catching the light of distant stars, a passenger on a journey that has no destination and no end. The tissues will remain intact, the form will remain recognizable, and time will pass in quantities that exceed our comfortable comprehension while the body simply waits, preserved by the very emptiness that surrounds it. And so we come now to consider the light itself, and the invisible rivers of particles that flow endlessly through the void, painting and weathering everything they touch with patient, cosmic hands. For space, you see, is not truly empty. And even in the profound stillness that exists between worlds, there are forces at work, quiet forces, persistent forces, forces that have been streaming through the universe since long before our sun first flickered into being, and these forces would find the drifting form and begin, in their own unhurried way, to leave their mark upon it. The story of how we came to understand these invisible cosmic messengers begins, fittingly enough, with a balloon, and with a curious Austrian physicist named Victor Hess, who in the years before the First World War became puzzled by a question that seemed, at first, rather simple. Scientists of that era had noticed that the air itself carried a small electrical charge, and they assumed this charge came from radioactive elements in the ground beneath their feet, from the uranium and radium and thorium that had been discovered in recent decades. But if this were true, Hess reasoned, then surely the charge would decrease as one moved away from the ground, would fade and diminish as one climbed higher into the atmosphere and left the radioactive Earth behind. And so, being a man of practical curiosity, he decided to test this assumption in the most direct way possible. Beginning in 1911 and continuing through 1912, Victor Hess undertook a series of balloon flights, ascending into the thin, cold air above Austria with his instruments and his questions, rising sometimes to altitudes of more than 5,000 meters, where the air grew sparse and breathing became difficult. And what he discovered there, high above the farms and villages and snow-capped peaks of his homeland, was something quite unexpected, something that would reshape our understanding of the universe in ways he could not have imagined. Rather than decreasing with altitude, the electrical charge in the air actually increased, grew stronger as he climbed higher, suggesting that something was streaming down from above, something arriving from beyond the atmosphere itself. He called them cosmic rays, these invisible visitors from the depths of space, and for this discovery, for this patient work of ascending into the sky and measuring what he found there, Victor Hess was awarded the Nobel Prize in Physics in 1936, recognition of a discovery that had opened a window into the violent and energetic processes occurring throughout our galaxy and beyond. We understand now that these galactic cosmic rays are not rays at all, in the ordinary sense of the word, but rather particles, fragments of atoms that have been accelerated to tremendous velocities by the magnetic field surrounding distant stars and by the shock waves of exploding supernovae and by processes we do not yet fully comprehend. They arrive at our solar system from all directions, these ancient travelers, some of them having journeyed for millions of years across the vast emptiness between the stars, and they carry energies that dwarf anything we can produce in our most powerful particle accelerators. Most of them are simply the nuclei of hydrogen atoms, single protons stripped of their electrons and moving at speeds approaching that of light itself. But some are heavier, nuclei of helium and carbon and iron, fragments of stars that died long ago in distant regions of the galaxy. And when they encounter matter, when they strike the atoms and molecules of a physical object, they do not pass through gently but rather tear and disrupt and ionize, leaving trails of damage in their wake, breaking molecular bonds and altering the very structure of the materials they penetrate. The Earth, of course, is protected from these cosmic visitors by the embrace of its magnetic field, which deflects and channels the charged particles, guiding them toward the polar regions where they occasionally paint the sky with the shimmering curtains of the aurora. And beneath this magnetic shield, we are further protected by the atmosphere itself, by the thick blanket of air that absorbs and scatters the remaining radiation, so that by the time it reaches the surface where we live and breathe, it has been reduced to a gentle murmur, a faint whisper of its former intensity. But in space, beyond the protection of our planet's magnetic embrace, the full force of these cosmic rays is felt, and anything exposed to them, any material, any organic matter, any drifting form, must endure their constant, penetrating attention. There is also the Sun to consider, our own familiar star, which despite its appearance of steady, golden calm is in fact a roiling furnace of nuclear fire, constantly exhaling a breath of particles that streams outward in all directions, filling the solar system with what we have come to call the solar wind. This wind is composed primarily of electrons and protons, The broken fragments of hydrogen atoms heated so intensely in the Sun's outer atmosphere that they escape its gravitational pull and rush outward into space at velocities that seem almost impossible to comprehend, typically between 400 and 750 kilometers per second, which means that a particle leaving the Sun's surface would reach the Earth, some 150 million kilometers distant, in just a few days. During periods of heightened solar activity, during the flares and coronal mass ejections that occasionally erupt from our star's turbulent surface, these speeds can increase further still, and the density of particles can rise dramatically, creating storms of radiation that sweep through the inner solar system like invisible hurricanes. We have known about this solar wind since the late 1950s. When the first spacecraft began to venture beyond Earth's atmosphere and detected its constant presence, confirming theories that had been proposed by astronomers studying the behavior of comet tails, which always stream away from the Sun regardless of the comet's direction of travel. And we have learned that this wind is not uniform, not constant, but varies with the Sun's 11-year cycle of activity, rising and falling in intensity as sunspots appear and fade on our star's visible surface. A body drifting in space would be bathed in this solar wind continuously, would be subject to its gentle but persistent pressure, would feel its particles striking and penetrating, adding their own contribution to the gradual weathering that cosmic rays begin. There are places, even within the protective envelope of Earth's magnetic field, where this radiation penetrates more deeply than elsewhere, and one such place has been studied extensively since its discovery in 1958, in the early days of the space age, when satellites first began to map the radiation environment surrounding our planet. This region, known as the South Atlantic Anomaly, lies over the southern Atlantic Ocean and extends across portions of South America. And here the Earth's magnetic field dips closer to the surface than anywhere else on the planet, creating a weakness in our cosmic shield through which radiation seeps more readily. Astronauts aboard the International Space Station notice increased radiation exposure when they pass through this region, and sensitive electronic equipment must sometimes be powered down to prevent damage. And the existence of this anomaly reminds us that even our planetary defenses are not perfect. That radiation is a constant presence in the space environment, patient and pervasive and relentless in its effects. Among the many forms of radiation that would reach a drifting form, ultraviolet light deserves particular attention. For unlike the particle radiation of cosmic rays and solar wind, ultraviolet radiation is a form of electromagnetic energy, a portion of the Sun's light that lies just beyond the violet edge of the visible spectrum, invisible to our eyes but carrying enough energy to break the chemical bonds that hold molecules together. Here on Earth, most of this ultraviolet radiation is absorbed by the ozone layer high in our atmosphere, which is why we can spend time in sunlight without immediately suffering severe damage to our skin and eyes, though even the small fraction that reaches the surface can cause sunburn and, over time, more serious effects. In space, without this protective ozone shield, the full intensity of solar ultraviolet radiation reaches any exposed surface, and its effects are both swift and cumulative. The Hubble Space Telescope, that magnificent instrument orbiting high above our atmosphere since 1990, has provided us with direct evidence of what ultraviolet radiation does to materials exposed in space. The telescope's solar panels, which unfold like great wings to capture sunlight and convert it to electrical power, are covered with thermal blankets designed to protect the delicate electronics beneath. And over the years of Hubble's operation, astronauts visiting the telescope during servicing missions have observed these blankets degrading, cracking, becoming brittle and fragmenting under the constant bombardment of solar radiation. The polymers from which these blankets were made, carefully engineered materials designed to withstand the harsh environment of space, nonetheless succumbed to the relentless breaking of their molecular bonds, the slow destruction of the long-chain molecules that gave them their flexibility and strength. If engineered materials designed specifically for space exposure degrade in this way, we can understand how much more vulnerable organic materials would be, how much more readily the complex molecules of biological tissue would be disrupted and transformed. What happens to proteins under such radiation is a process not entirely unlike tanning, the ancient craft of turning animal hides into leather, though the space environment accomplishes something rather more extreme. In traditional leather tanning, the proteins of the hide are treated with chemicals, often derived from tree bark, that cause the long protein molecules to form additional chemical bonds with one another, linking together in ways that make the material stiffer, more durable, less susceptible to decay. This process is called cross-linking, and radiation, particularly ultraviolet radiation, induces a similar effect in any proteins it encounters. The energy of the ultraviolet photons breaks existing bonds and creates highly reactive molecular fragments that then form new bonds with neighboring molecules, linking proteins together in a dense, tangled network that bears little resemblance to the original, flexible, living tissue. The result is a material that is harder, more brittle, darker in color, and far more resistant to biological decay than the tissue from which it formed, a kind of accidental preservation achieved through chemical transformation rather than intention. The sun-facing side of a drifting form would experience this process most intensely, would be bathed in the full glare of unfiltered solar radiation, while the shadow side, turned away from the sun, would remain in darkness, receiving only the scattered glow of distant stars and the faint reflected light from any nearby bodies. The temperature difference between these two sides would be remarkable, potentially exceeding 250 degrees Celsius, with the sunlit surface reaching perhaps 120 degrees Celsius or more, while the shadowed surface plunged to perhaps 150 degrees below zero. This stark thermal gradient would create stresses in the tissues, as materials expanded on the hot side and contracted on the cold side, and over time these stresses would contribute to cracking and fragmentation, adding mechanical weathering to the chemical and radiological processes already at work. We have direct evidence of how materials behave under long-term exposure to the space environment, thanks to an experiment called the Long Duration Exposure Facility, or LDEF, a large cylindrical satellite placed in orbit by the Space Shuttle Challenger in 1984 and retrieved, after an unexpectedly extended mission, by the Space Shuttle Columbia in 1990. Originally intended to remain in space for less than a year, the Challenger disaster of 1986 delayed the retrieval mission, and LDEF ultimately spent nearly 6 years orbiting the Earth, its many surfaces and sample trays exposed to the full range of space environmental factors. When scientists examined the retrieved samples, they found extensive degradation of organic materials, polymers that had become brittle and discolored, surfaces that had been eroded and pitted, clear evidence of the cumulative damage inflicted by years of exposure to radiation and atomic oxygen and the other hazards of low Earth orbit. The skin of a drifting form, that thin outer layer that once served as the boundary between self and environment, would undergo similar changes, but with the added complexity of its organic composition. It would darken, first, as the radiation induced changes in the pigments and proteins of the outer layers, Then it would begin to crack as cross-linking made it progressively more brittle. And eventually it would take on a texture not unlike dried leather that has been left too long in harsh sunlight. Though this comparison does not fully capture the extreme nature of the transformation. The cells, long since frozen and desiccated, would lose their individual identity, their membranes breaking down and their contents merging into a dense, darkened matrix, and the overall surface would become something quite unlike living skin, something more mineral than biological in its appearance and texture. And there is one more factor to consider in this slow process of cosmic weathering, one that operates on the longest timescales of all, and this is the gentle but persistent bombardment by micrometeorites. Those tiny grains of cosmic dust that drift through the solar system in countless billions, fragments of asteroids and comets, and perhaps even material from beyond our solar system entirely. These particles are small, often no larger than grains of sand or pollen, but they travel at tremendous velocities, typically between 10 and 70 kilometers per second. Which means that even a tiny grain carries significant kinetic energy, enough to excavate a crater many times its own diameter when it strikes a surface. Over the course of millennia, these impacts would slowly erode any exposed surface, pitting and cratering it in a process not unlike the wind erosion that shapes desert rocks here on Earth, though accomplished through impact rather than abrasion. The effect would be gradual, almost imperceptible on human timescales, but over thousands and millions of years, it would become significant, slowly wearing away the outer layers of the drifting form, exposing fresh material beneath only to have that material weathered in turn. Combined with the radiation effects and the thermal cycling and all the other processes we have discussed, this micrometeorite bombardment would contribute to a slow but inexorable transformation, a gradual merging of the form with its environment, until eventually, given sufficient time, there would be little left but scattered dust, minerals, and simple compounds distributed through the void. The complex organization of a human body returned to the simple elements from which it was first assembled, billions of years ago, in the hearts of dying stars. And so the body would drift, painted by starlight, weathered by cosmic wind, transformed by processes that operate on timescales far beyond the brief span of a human life, becoming, gradually, part of the vast and patient universe itself. And now we come to consider the longer journey, the quiet question of where exactly a body might travel once it has left the familiar confines of our world. And this is a question that belongs not to the realm of speculation but to the ancient and patient discipline of orbital mechanics, a field of study that concerns itself with the predictable paths of all things moving through the gravitational fields of larger bodies. And it is here that we find ourselves in the company of Johannes Kepler, the German astronomer who, in the year 1609, published his first 2 laws of planetary motion, observations that emerged from his painstaking analysis of the orbit of Mars using data collected by his predecessor Tycho Brahe. And these laws tell us something quite beautiful in their simplicity, namely that all objects in orbit trace elliptical paths with the larger body at one focus of the ellipse, and that a line drawn between the orbiting object and the central body will sweep out equal areas in equal times, which is to say that objects move faster when they are closer to what they orbit and slower when they are farther away. And these principles, refined by Isaac Newton some decades later and extended by countless mathematicians since, govern the motion of everything from the Moon to the smallest fleck of paint drifting in low Earth orbit. And they would govern equally the motion of a human body set adrift in the vastness beyond our atmosphere. Let us begin close to home, at the altitude where the International Space Station conducts its perpetual falling around the Earth, approximately 400 kilometers above the surface. And if we imagine a body released here, perhaps during an extravehicular activity or in the aftermath of some quiet incident, we might wonder how long that body would continue its orbital journey before returning to Earth. And the answer, perhaps surprisingly, is not terribly long at all. For even at this altitude there remains a whisper of atmosphere. Molecules of gas so sparse that they would be considered a hard vacuum by any earthly standard, yet present enough to exert a gentle drag on anything passing through them. And this drag, imperceptible moment to moment, accumulates over weeks and months to gradually lower the orbit of any object, bringing it ever closer to the thicker atmosphere below, and depending on solar activity, which causes the upper atmosphere to expand and contract. A body released at 400 kilometers would likely re-enter the atmosphere within a span of months to a few years, eventually heating and fragmenting as it encountered denser air. And so the story of such a body would be a relatively brief one in cosmic terms. A gentle spiraling return to the planet from which it came. The question of how long debris can persist in orbit has been studied with some care by specialists concerned with the growing population of objects circling our world. And among these researchers we find Dr. William Ayler of the Aerospace Corporation, an organization dedicated to providing technical guidance on space systems. And in 2006, calculations by orbital mechanics specialists, including work associated with such experts, examined the expected longevity of objects at various altitudes. And what emerges from these studies is a picture of dramatically different fates depending on where an object finds itself. For at lower altitudes the atmospheric drag ensures relatively quick decay, while at higher altitudes, above perhaps 1,000 kilometers, objects may persist for centuries or even millennia, their orbits so far from any significant atmospheric resistance that only the most subtle perturbations from gravitational irregularities and solar radiation pressure will alter their paths over vast stretches of time. And so a body released at greater altitude would embark upon a much longer journey, circling the Earth in patient silence while generations lived and passed on the surface below. If we imagine our drifting body released not in low Earth orbit but at the distance of the Moon, some 384,000 kilometers from Earth, or beyond, we enter a different regime entirely, one where the gentle drag of atmosphere plays no role whatsoever and where the dynamics become those of the Sun and the planets rather than Earth alone. And here a body might find itself in a stable or quasi-stable orbit around the Sun, tracing its own elliptical path through the inner solar system much as the asteroids do. And in such a configuration it might persist not for years or centuries but for millions or even billions of years, a silent companion to the planets on their ancient rounds. And the mathematics that describe this possibility are the same mathematics that Kepler and Newton gave us, extended and refined but fundamentally unchanged. The clockwork of gravity playing out on timescales that dwarf all of human history. There is a gentle precedent for human remains traveling beyond the Earth, and it involves a remarkable man named Eugene Shoemaker, who was a geologist and planetary scientist of considerable accomplishment, a pioneer in the study of impact craters who trained Apollo astronauts to understand the lunar landscape they would walk upon. And Shoemaker had dreamed of traveling to the Moon himself but was prevented from becoming an astronaut due to a medical condition. And when he passed away in 1997, a small portion of his ashes was placed aboard the Lunar Prospector spacecraft, which launched in 1998 on a mission to study the Moon from orbit. And when that mission concluded, the spacecraft was deliberately impacted into a crater near the lunar South Pole, carrying Shoemaker's ashes with it. And so Eugene Shoemaker became, in a manner of speaking, the first human to have any part of themselves come to rest on another world. a fitting tribute to a man who had devoted his life to understanding the surfaces of planets and moons. And his remains lie there still, in the cold grey regolith of a permanently shadowed crater, undisturbed by wind or weather, a quiet memorial that will persist for longer than we can readily comprehend. Now let us consider certain special locations in the gravitational landscape of any two-body system, points of equilibrium discovered by the mathematician Joseph Louis Lagrange in 1772. And these points, 5 in number for any pair of massive bodies such as the Earth and Sun or the Earth and Moon, represent positions where the gravitational forces and the centrifugal effects of orbital motion combine in such a way that a small object placed there will tend to remain, orbiting the Sun in lockstep with the Earth rather than drifting away. And the most stable of these points, designated L4 and L5, lie along the Earth's orbit 60 degrees ahead of and behind our planet, forming equilateral triangles with the Earth and Sun. And objects at these locations can remain there for extraordinarily long periods, which is why Jupiter's L4 and L5 points are home to the Trojan asteroids, thousands of small bodies that have been trapped there for billions of years. And while no human remains have been placed at a Lagrange point, one can imagine such a location as a kind of gravitational eddy in the river of orbital motion, a place where a drifting body might find itself in a stable configuration for timescales that approach the age of the solar system itself, neither falling toward the Sun nor spiraling outward but simply maintaining its position in that delicate balance of forces. For a body released on an escape trajectory, one with sufficient velocity to leave the Earth-Moon system entirely and venture into interplanetary space, the mathematics predict an even longer journey. And here we have a human-made example in the spacecraft Voyager 1, which was launched in 1977 and has since become the most distant human-made object, having traveled more than 24 billion kilometers from the Sun and continuing outward at a speed of roughly 17 kilometers per second. And this spacecraft, which carries a golden record containing sounds and images of Earth as a message to any intelligence that might someday encounter it, will not approach another star for tens of thousands of years. For the distances between stars are so vast that even at such speeds the journey is measured in millennia. And current calculations suggest that Voyager 1 will pass within approximately 1.6 light-years of a small red dwarf star called Gliese 445, which lies in the constellation Camelopardalis, in about 40,000 years. And by then the star will have moved somewhat closer to our Sun due to its own motion through the galaxy, and Voyager will drift past at a distance that is still enormous by any human standard. And then it will continue onward into the galaxy, a tiny emissary from a small planet, its instruments long since silent but its physical form persisting for longer than we can readily imagine. A human body set on a similar trajectory, escaping the solar system entirely, would undertake a journey of comparable duration and distance, drifting through the interstellar medium for millions and eventually billions of years, its form gradually modified by cosmic ray bombardment and the occasional impact of interstellar dust but never truly disappearing. For in the void between stars there is so little material and so few forces acting that change comes with almost inconceivable slowness. And such a body would outlast the Earth itself. For in approximately 5 billion years our Sun will exhaust the hydrogen fuel in its core and swell into a red giant, expanding outward to engulf the inner planets and rendering Earth uninhabitable long before that final expansion. And yet a body drifting in interstellar space, far from any star, would be untouched by this transformation, continuing its patient journey through a galaxy that itself continues to evolve. Stars being born and dying, the great spiral arms rotating slowly over hundreds of millions of years. For a body that remains within the solar system but beyond the reach of any planet's gravity, The most likely fate is a long orbit around the Sun, an ellipse that might take it from the inner solar system out past the orbit of Mars or Jupiter and back again, a journey that could repeat essentially unchanged for billions of years. The body becoming in effect a very small and very quiet asteroid, one more member of the countless population of small objects that circle our star. And over such immense timescales, there is a small but non-zero probability of gravitational encounters with planets that might alter the orbit, eventually leading either to ejection from the solar system entirely or to a collision with a planet or the Sun itself. But the mathematics of orbital mechanics suggest that for many initial conditions the orbit would remain stable for timeframes comparable to the remaining life of the solar system, which is to say several billion years. And so we arrive at the curious conclusion that a human body, properly placed in space, might endure longer than the civilization that produced it, longer than the species from which it came, longer perhaps than the planet Earth itself. This is the choreography of forever, the slow and stately dance of objects moving under the influence of gravity alone, following paths that were first understood by observers working with pen and paper in the 17th and 18th centuries, paths that were old when the Earth was young and that will continue long after everything we know has changed beyond recognition. And there is something restful in this knowledge, something calming in the understanding that the forces governing such motion are entirely predictable and entirely indifferent, that gravity asks nothing of the objects it guides and judges nothing about their origin or purpose, but simply bends their paths according to the same mathematical relationships that govern the motion of galaxies and the fall of a dropped stone. And in this democracy of physics, a drifting human body becomes simply another small mass responding to the curved geometry of space-time, tracing its ellipse or hyperbola with the same fidelity as any planet or comet, and it will continue to do so for as long as the Sun shines and beyond, patient and unhurried, keeping time with the oldest rhythms in the universe. And so we arrive, gently now, at the longest timescales of all, the spans of time that stretch beyond anything we might ordinarily contemplate, beyond the rise and fall of empires, beyond the slow grinding of mountains into dust, beyond even the patient drift of continents across the face of the Earth. We have followed our quiet traveler through the first moments, the first hours, the first years of their solitary journey, and now we must consider what remains when thousands of years have passed, when millions of years have accumulated like soft snow upon a silent landscape, when time itself becomes almost meaningless in its enormity. To understand what persists across such vast durations, it helps to consider first what we have learned from remains much closer to home, from bodies that have survived not in the vacuum of space but in the cold embrace of terrestrial ice. In 1991, high in the Ötztal Alps along the border between Austria and Italy, two German hikers made a discovery that would reshape our understanding of preservation and time. There, emerging from a melting glacier at an elevation of some 3,200 meters, lay the remarkably intact remains of a man who had died approximately 5,300 years ago. He would come to be known as Ötzi the Iceman, and his body would teach us extraordinary things about the boundaries of biological persistence. Ötzi's preservation was, in many ways, a series of fortunate accidents. He died in a sheltered hollow, was quickly covered by snow, and remained frozen within the glacier for more than 5 millennia. His skin survived, his internal organs survived, even the contents of his stomach survived, revealing his final meals of ibex meat and einkorn wheat. Scientists could determine that he suffered from Lyme disease, that he had arthritis in his joints, that he had eaten a meal rich in animal fat not long before his death. The cold had acted as a kind of pause button, slowing the chemical reactions that would otherwise have dismantled his tissues molecule by molecule, allowing him to persist through ages that saw the rise of ancient Egypt, the flourishing and collapse of Rome, the entire medieval period, and the Industrial Revolution. What made Otz's preservation possible was primarily the absence of liquid water and the suppression of microbial activity through cold. And here we begin to see why our traveler in space might, paradoxically, persist even longer than Otzi did in his alpine tomb. For the vacuum of space offers something that even the coldest glacier cannot provide, which is a complete absence of the very medium through which most degradation occurs. The molecule that carries our genetic information, deoxyribonucleic acid, is famously fragile over long timescales. In typical terrestrial environments, DNA degrades through two primary mechanisms: hydrolysis and oxidation. Hydrolysis, as the name suggests, requires water, and it occurs when water molecules insert themselves into the bonds that hold the DNA backbone together, gradually snipping the long strands into shorter and shorter fragments. Oxidation occurs when reactive oxygen species attack the nucleotide bases, chemically altering them in ways that obscure the genetic information they once carried. Together, these processes mean that under normal conditions, DNA becomes unreadable within tens of thousands of years at most. But in 2013, a research team led by Dr. Ludovic Orlando at the University of Copenhagen published findings that challenged our assumptions about the limits of DNA survival. Working with horse bones recovered from permafrost in the Yukon, bones that had been frozen for approximately 700,000 years, the team successfully extracted and sequenced fragments of ancient DNA. This was, at the time, the oldest DNA ever recovered, and it demonstrated that under sufficiently cold and dry conditions, genetic material could persist for timescales that had previously seemed impossible. The key was the suppression of both hydrolysis and oxidation, the removal of liquid water and the limitation of reactive oxygen species. Our traveler, drifting through the deep cold of interstellar space, exists in an environment that suppresses both of these degradation pathways more completely than any terrestrial setting. There is no liquid water to drive hydrolysis, and while cosmic radiation does provide oxidative stress, the temperature is so extraordinarily low that even radiation-induced damage accumulates slowly. The chemical reactions that would unmake DNA on Earth proceed at rates governed by temperature, and at temperatures approaching absolute zero, those rates slow to an almost imperceptible crawl. It is possible, though by no means certain, that fragments of our traveler's genetic material might persist for millions of years, frozen in a state of near-perfect chemical stasis. But even if the DNA eventually degrades beyond all recognition, even if every organic molecule eventually succumbs to the patient accumulation of radiation damage, there are structures that would remain essentially unchanged. The mineral component of bone, a crystalline substance called hydroxyapatite, is extraordinarily stable. It is, in chemical terms, a form of calcium phosphate, and it forms the hard matrix that gives bones their strength and rigidity. In the absence of water, acids, and the relentless biological recycling that occurs on Earth, hydroxyapatite could persist indefinitely in the vacuum of space. The scaffold of our traveler's skeleton, stripped of its organic components, would remain as a kind of three-dimensional map of a human form: the proportions of the limbs, the curvature of the spine, the shape of the skull, all preserved with a fidelity that would survive the death of stars. And the teeth, those small and unassuming structures that we so rarely contemplate, would survive longest of all. Human teeth are approximately 96% mineral, mostly a variant of hydroxyapatite called apatite, and they are among the most durable biological structures in existence. On Earth, teeth routinely survive for millions of years in the fossil record, and in space, where there is no groundwater to dissolve them, no sediment pressure to crush them, no scavenging organisms to scatter them, they would persist essentially forever. Our travelers' dental structure, the number and arrangement of their teeth, the wear patterns from a lifetime of chewing, perhaps even the chemical signatures of the foods they ate, would remain readable across spans of time that defy human comprehension. This brings us to a thought that occupied the mind of one of the 20th century's most gifted science communicators. In 1977, the astronomer and author Carl Sagan served as the chairman of a committee tasked with creating a message that would accompany the Voyager spacecraft on their journeys to the outer solar system and beyond. The result was the Voyager Golden Record, a phonograph record made of gold-plated copper, containing sounds and images selected to portray the diversity of life and culture on Earth. The record included greetings in 55 languages, music from around the world, and a collection of 116 images depicting human anatomy, scientific knowledge, and scenes of terrestrial life. Sagan understood that the spacecraft themselves might survive for billions of years in the emptiness between stars, and he wanted to ensure that if any intelligence ever encountered them, they would find not merely a machine but a message, a deliberate attempt at communication across the vast loneliness of the cosmos. Our traveler carries no golden record, no carefully curated collection of human achievement. But they carry something perhaps equally informative, which is the physical record of a human life inscribed in bone and tooth and crystallized tissue. The chemical composition of their remains would tell a story to any intelligence capable of reading it. The ratio of certain isotopes in their bones would reveal the approximate latitude at which they lived, because these ratios vary with climate and geography. The trace elements in their teeth would record the water they drank and the soil in which their food was grown. The wear patterns on their molars would speak to their diet, whether they ate primarily soft or hard foods, whether they consumed significant amounts of gritty material. Even the shape of their bones would carry information, the muscle attachment sites revealing the kinds of physical activities they performed in life. The astrobiologist Paul Davies, in his writings on the search for extraterrestrial intelligence and the nature of biological signatures, has explored the question of what an alien observer might learn from biological remains. Davies notes that chemistry is universal, that the elements that compose a human body are the same elements found throughout the cosmos, and that an intelligent observer could, in principle, work backward from those elements to understand something of the environment that produced them. A body is, in this sense, an environmental record, a chemical diary of a world and a way of life. If our traveler were ever found, drifting in the space between stars or captured by the gravity of some distant world, their remains would constitute an unintentional time capsule of extraordinary richness. An observer with sufficient analytical capability could determine that this was a carbon-based life form, that it relied on oxygen-dependent metabolism, that it consumed other life forms for sustenance. They could determine approximate body mass and height, could infer the gravity of the world on which the traveler evolved, could perhaps even reconstruct aspects of the microbial community that once inhabited the traveler's digestive system from trace chemical signatures. The body would speak, in the universal language of chemistry and physics, of a world with liquid water, an oxygen-rich atmosphere, and an ecosystem of sufficient complexity to support large, mobile organisms. There is, in all of this, a profound and somehow comforting thought. Our civilizations are, in the grand sweep of cosmic time, extraordinarily fragile things. The cities we build will crumble. The languages we speak will be forgotten. The digital archives in which we store our knowledge will degrade and fail. 1,000,000 years from now, there may be no trace of human civilization remaining on Earth. No evidence that we ever built, or dreamed, or wondered about our place in the universe. But a body adrift in space, preserved by the cold and the vacuum, might persist for timescales that dwarf the entire history of human culture. We might survive longer as unintentional artifacts than as the intentional creators of artifacts. This is not a melancholy thought, or at least it need not be. There is something almost peaceful in the idea that the cosmos preserves what civilizations cannot, that the cold and patient darkness might carry forward some record of our existence long after our works have turned to dust. Our traveler, whoever they were, becomes in their silent journey a kind of ambassador, not in the deliberate sense that Sagan intended with his golden records, but in a more fundamental sense, as a physical embodiment of what it meant to be human in this particular time and place. The message they carry is written in hydroxyapatite and carbon isotopes, in trace elements and crystalline structures. It is a message that requires no translation, because it is written in the universal grammar of matter and energy, of atoms and molecules, of the physical laws that govern all things everywhere. And it is a message that will endure, quietly and patiently, through spans of time that we can scarcely imagine, waiting for a reader who may never come, but who would find, if they did, a faithful record of one small life on one small world in one small corner of an incomprehensibly vast and ancient universe. And so our traveler drifts on, through the long silence between the stars, carrying their message into the cosmic ocean, a bottle thrown into waves that stretch from here to the edge of the observable universe and beyond. And so, as we near the end of our journey tonight, let us gently lift our gaze away from the immediate concerns of tissue and temperature, away from the particulars of sublimation and the quiet patience of mummification, and let us instead allow our perspective to expand outward, slowly and peacefully, toward something far grander and more ancient than any single human story. Because when we speak of a body adrift in the deep black, we are not merely discussing an ending, but rather a return, a homecoming of sorts, to the very source from which we all emerged so very, very long ago. The astronomer Carl Sagan, in his celebrated 1980 series Cosmos, offered us a phrase that has since become woven into the fabric of how we understand ourselves and our place in this vast universe. He reminded us, with characteristic gentleness and awe, that we are made of star stuff, that the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, were all manufactured in the interiors of collapsing stars. This was not poetry dressed as science, nor science reaching toward poetry, but simply the truth, expressed with the kind of quiet wonder that such truths deserve. And tonight, as we contemplate the ultimate fate of a human form left to drift among those very stars, it seems only right that we return to this idea, and allow it to settle over us like a warm and familiar blanket. You see, every atom in your body, without exception, has a history that stretches back billions of years before you were born, before your parents were born, before the Earth itself had coalesced from the swirling disk of gas and dust that surrounded our young sun. The carbon atoms that form the backbone of every organic molecule within you, the oxygen atoms that your cells use to generate energy, the nitrogen atoms woven into your proteins and nucleic acids, none of these were present at the very beginning of the universe. In those first frantic moments after the Big Bang, some 13.8 billion years ago, the cosmos was too hot, too energetic, too chaotic to permit the formation of anything heavier than the simplest elements. There was hydrogen, yes, vast quantities of hydrogen, and there was helium, and trace amounts of lithium, but nothing more. No carbon, no oxygen, no iron, no gold. The periodic table, as we know it today, was almost entirely empty. And so the universe, in its patient and unhurried way, set about filling in those gaps, not through any single cataclysmic event, but through the slow and steady work of countless stars living and dying across billions of years. This process, which scientists call stellar nucleosynthesis, is one of the most beautiful and profound stories that physics has to offer us, and it was first told in comprehensive detail in a landmark paper published in the year 1957. That paper, often referred to by the affectionate shorthand B²FH, was the work of four remarkable scientists whose names deserve to be spoken gently and with gratitude as we drift towards sleep. They were Fred Hoyle, the brilliant and sometimes controversial English astronomer who had been thinking about element formation in stars since the 1940s, Margaret Burbidge, an extraordinary observational astronomer who overcame tremendous barriers placed before women in science during her era, her husband Geoffrey Burbidge, a theoretical astrophysicist of great insight, and William Fowler, a nuclear physicist whose experimental work provided crucial support for their theoretical framework. Together, in 104 pages of careful reasoning and mathematical demonstration, they showed us how stars are the forges in which the elements of life are made. The process begins in the cores of stars, where temperatures and pressures are so extreme that hydrogen nuclei, simple protons, are forced together with such violence that they overcome their natural electromagnetic repulsion and fuse into helium. This is the reaction that powers our Sun today, and has done so for approximately 4.6 billion years, and will continue to do so for roughly another 5 billion years to come. But hydrogen fusion is only the first step in a much longer chain of nuclear transformations. As a star ages, as it exhausts the hydrogen in its core, it begins to contract under its own gravity, and this contraction raises the temperature and pressure still higher, until eventually the helium nuclei themselves begin to fuse, producing carbon and oxygen. And in the most massive stars, stars far larger than our Sun, this process continues further still, with carbon fusing to produce neon and magnesium, neon fusing to produce oxygen and magnesium, oxygen fusing to produce silicon and sulfur, and silicon fusing, in the final desperate days of the star's life, to produce iron. Iron, you see, is a kind of endpoint for stellar fusion, a dead end in the nuclear road, because fusing iron nuclei together does not release energy but rather requires it. And so when a massive star develops an iron core, it has reached a crisis from which there is no peaceful escape. Within moments, the core collapses, and the outer layers of the star come crashing down upon it, and then rebound outward in a catastrophic explosion that we call a supernova. And it is in the unimaginable violence of this explosion, lasting mere seconds but releasing more energy than our Sun will produce in its entire 10 billion year lifetime. That elements heavier than iron are forged, as free neutrons slam into existing nuclei and build up the heaviest atoms on the periodic table. The gold and platinum and uranium that we find scattered so sparingly through the Earth's crust. All of this stellar debris, the carbon and oxygen and nitrogen and iron and everything else, is flung out into the interstellar medium, where it mingles with the primordial hydrogen and helium that still pervades the galaxy. And gradually, over millions of years, this enriched gas begins to collapse under its own gravity, forming new stars and new planets and, in at least one case that we know of, new life. Our own solar system formed approximately 4.6 billion years ago from just such a cloud of recycled stellar material, and every atom heavier than helium that exists on Earth today, including every atom in your body, was processed through the interior of at least one star that lived and died before our Sun was born. Some of those atoms may have passed through multiple generations of stars, being ejected in one supernova only to be incorporated into a subsequent star that itself eventually exploded, each cycle adding new elements to the cosmic inventory. The iron in your blood may have been forged in a star that died 8 billion years ago, while the calcium in your bones might trace its origin to a different star that exploded 6 billion years before that. We cannot know the specific histories of individual atoms, of course, but we can say with confidence that your body, the body we have been contemplating tonight as it drifts through the eternal darkness, contains roughly 7 octillion atoms, that is, 7 followed by 27 zeros, and every single one of them carries within it a story billions of years in the telling. Now, as we consider the fate of this drifting form across truly cosmic timescales, let us remember that the universe is not static, that the stars themselves are mortal, that even our familiar Sun is slowly but inexorably changing. In approximately 5 billion years, give or take a few 100 million, our Sun will exhaust the hydrogen fuel in its core and begin the process of transformation that awaits all stars of its size. It will swell into a red giant, its outer layers expanding outward until they engulf the orbits of Mercury and Venus and very likely Earth as well. The inner solar system, everything we have ever known, will be vaporized and absorbed into the dying Sun's bloated atmosphere. Mars may survive, barely, as a scorched and barren rock, and the outer planets will endure in altered form, but the cradle of human civilization will be gone, returned to the stellar furnace from which it originally emerged. And yet, and here is a thought to carry with you gently into sleep, a human body drifting far enough from the Sun, out in the Oort cloud perhaps, or ejected entirely from the solar system into interstellar space, might well survive this cataclysm. Frozen, desiccated, reduced to a delicate shell of crystallized organic compounds and mineite, it would continue its silent journey through the darkness while the Sun swelled and subsided behind it, eventually collapsing into a white dwarf no larger than the Earth and beginning its own slow fade into obscurity. The body would drift on, patient and indifferent, while billions more years passed and the white dwarf cooled from brilliant white to yellow to red to the faint infrared glow of a stellar ember, and eventually, across timescales so vast that they strain the limits of meaningful comprehension, to the absolute cold of a black dwarf, a stellar corpse emitting no light at all. And still the journey would continue. The Milky Way and Andromeda would collide and merge, as they are destined to do in approximately 4.5 billion years, their stars passing through one another like ghosts, their central black holes eventually spiraling together and coalescing. New stars would form from the disrupted gas clouds, and old stars would die, and the merged galaxy would settle into a new and unfamiliar configuration. A drifting body, if it avoided being captured by any passing star or planet, would simply continue onward, a silent witness to transformations beyond anything we can easily imagine. The ultimate fate of the universe itself remains a subject of careful scientific investigation and gentle speculation, but the most widely accepted models suggest that we are heading toward what physicists call heat death, a state of maximum entropy in which all useful energy has been dissipated and no further work can be done. The timescale for this final quieting is almost incomprehensibly vast, estimated at something like 10 to the power of 100 years, a 1 followed by 100 zeros, a number so large that even calling it astronomical seems hopelessly inadequate. Long before that final darkness falls, the last stars will have burned out, the last black holes will have evaporated through the slow quantum process called Hawking radiation, and the universe will consist of nothing but a thin, cold soup of fundamental particles drifting ever farther apart as space itself continues to expand. Somewhere in that inconceivable future, the atoms that once assembled themselves into a human being, the carbon and oxygen and nitrogen and calcium and iron, will have long since gone their separate ways. Perhaps they were scattered by a chance encounter with another body, or disrupted by the tidal forces of a passing star, or simply eroded away by the patient bombardment of cosmic rays across trillions of years. It does not matter, really, how it happened. What matters is that those atoms, having briefly participated in the grand experiment of human consciousness, having briefly looked out at the universe and wondered at its beauty, will return to the cosmic cycle from which they came. They may find themselves incorporated into a future nebula, condensing once again into a new generation of stars and planets. They may become part of a future world, perhaps a world where new forms of life arise and begin their own journey of discovery and wonder. The probability of any given atom from your body ending up in any specific place is vanishingly small, of course, but across enough time and enough space, all things that can happen eventually will. And so we arrive at the gentle heart of our meditation tonight. A human body adrift in space is not an ending but a transition, not a loss but a return. The star stuff that briefly coalesced into bone and blood and brain will eventually rejoin the great reservoir of matter from which all things are made, carrying with it, in some sense that perhaps only poets can fully articulate, the memory of having once been alive, of having once loved and dreamed and looked up at the night sky with curiosity and hope. We are, all of us, temporary arrangements of ancient matter, and there is something profoundly peaceful in knowing that the atoms which compose us will go on, will continue their eternal dance through the cosmos, will perhaps one day be part of something new and wonderful that we cannot begin to imagine. The journey continues, as it always has, as it always will, and we are privileged beyond measure to be conscious participants in it, even if only for a little while. So let this knowledge settle gently over you as you drift toward sleep, like the soft light of distant stars falling through an open window. You are connected to the cosmos in the most intimate and literal way possible. You are made of stars, and to the stars you will one day return, and in between, you have the extraordinary gift of being aware of it all, of feeling wonder, of feeling peace. The universe is vast and ancient and full of quiet beauty, and you are part of it, now and always. Rest well.